Hello, everyone. It's my pleasure today to meet you. I am here in Baku, in Azerbaijan. I don't know if there is anybody from Azerbaijan there. Raise your hand so I can see you. Oh, great. Hi. Hello, everyone. So I'm here for a meeting of EPAC. It's the Eastern European network, and it's a building connections conference, and I'm here as invited by the Azeri Academy of Sciences. So it's really an honor to be here, and it's an honor to meet you there as invited by the Turkish Academy of Sciences. So today is really about making connections, I think. So today I would like to talk to you about CERN, space and science diplomacy. I saw that also on your on the program there are other talks about CERN. So I hope you learned already a little bit about CERN and what it does. So today I will tell you more about space and science diplomacy. So let me close this window so I think you can see better here. Okay, so what we do at METU is the Middle East Technical University in Ankara. We are an astroparticle physics group, and we have two legs. One of these legs is the fundamental science perspective, and the other one is the applied research perspective. So on the fundamental science perspective, what we do is we work with the International Space Station on the AMS-02 experiment, and the alpha magnetic spectrometer is a detector up on the International Space Station, and we measure cosmic rays and we search for a dark matter signal. As for our applied research side, what we do is we work with METU-DBL, and METU-DBL is the METU defocusing beamline project. And what we do is we predict radiation doses for our national satellites, and we do radiation tests with 15 to 30 MeV protons according to the European Space Agency standard. Our group is large. It's 6 physicists, 5 engineers, 2 technicians, 3 administrative staff, and I have 5 PhD students as well as 5 master students. So now I will tell you this in more detail and how this relates to science diplomacy. So what we study is we study cosmic rays. What are cosmic rays? Cosmic rays are primaries, and these are mostly protons, and they travel very close to the speed of light, and they come from space. What do I mean by space? I mean primarily, of course, from our sun, but not just our sun, from stars, from matter that falls into black holes, from neutron stars, from other exotic objects out there in space. And these objects, as they shine, accelerate protons and electrons very close to the speed of light, much beyond what we can do at CERN. And they come and they hit our atmosphere. When they hit our atmosphere, they of course hit the oxygen and the nitrogen molecules in our atmosphere, and they cause showers. These showers are showers of particles, of subatomic particles. And here you may or may not have heard of some of them, such as pions and muons, kaons. And these exotic particles then decay into the few subatomic particles that are common. What do I mean by that? I mean, eventually they decay into protons and electrons. And when we fly through this. For example, here is an airplane, and when we fly through this. Generally, when we fly, we get about 10 times more the amount of radiation rate that we get while we are on Earth. And because we're flying through the shower. So this shower was discovered a while back in the 1910s by Professor Hess. And since then, it's been interesting to study because we have learned a lot about cosmic rays. For example, antiprotons were first discovered in cosmic rays, as well as positrons. So there has also been 4 Nobel Prizes awarded to discoveries using cosmic rays. So we continue understanding cosmic rays, but now we have moved this to space. Why have we moved to space? So because we don't want the overburden of the atmosphere. So here is AMS-02. This is the International Space Station. For those of you who may not know, the International Space Station is about 400 kilometers above the Earth, It goes around the Earth 18 times a day. It has very large solar panels, as you see here. These are huge solar panels. And the AMS experiment, the alpha magnetic spectrometer, which I helped build while I was at MIT, is situated on this International Space Station truss. And astronauts and cosmonauts and other space humans live here in these quarters in the center. And the International Space Station provides our power, cooling, as well as data transfer to the Earth. We have been taking data up on the International Space Station since May 2012. So here is a photo of the alpha magnetic spectrometer. The alpha magnetic spectrometer was built by a collaboration of countries around the Earth, 15 countries, but everything came together at CERN. So the integration was done at CERN, as well as testing and making sure that we could see particles in space. So it is large. It's 15 feet by 12 feet by 9 feet, and it's 7.5 tons, which is huge by space standards. And there are 300,000 electronic channels on this giant, by space standards again, detector. And there are 650 processors. And this detector is actually very similar to the other detectors at CERN, at the Large Hadron Collider. So at the Large Hadron Collider, there are, for example, ATLAS and CMS. And the detectors that we have on the International Space Station are very similar in quality and quantity to what you see at the Large Hadron Collider at CERN. So we went to space using the Space Shuttle, which is now retired, which has since retired. This is the Space Shuttle, which used to go up like a rocket, but then land as a plane. And we were in the cargo bay. So the cargo bay of this plane looking like rocket was in the back of this space shuttle called Endeavour. And here we are in Endeavour's cargo bay as we went up to space. Here is the astronauts that took us to space in 2012. And the liftoff was from Kennedy Space Center. And you see here, this was very different than what we are probably seeing now, watching now from SpaceX. Endeavour went up like a rocket, but it carried cargo and humans at the same time. This strategy has now been abandoned. Now, for example, SpaceX and other Blue Origin and others now carry either cargo or human. Why is it different? Because the requirements for safety for the cargo and for humans is significantly different. And if you are carrying humans, you have to be much more careful with safety. For cargo, you can be a bit more relaxed. But in the days of the space shuttle, these requirements were one and the same. So here this gives you a feeling, I hope, for space flight. This Endeavour, this shuttle, was 110 tons. This external tank, this tank that you see, this orange tank that you see here, which burnt liquid oxygen and liquid hydrogen into water, was 756 tons. The solid rocket boosters on the sides, the two sides you see here, the two rockets on the both ends, these were 1,142 tons, and the total weight of this, was totaling 2,000 tons. Why? This only carried AMS, which is in the back, of 7.5 tons, and 6 astronauts to space. So you see, this is why now space is being disrupted, as this weight ratio, the ratio of your payload versus the total weight at liftoff, is what rocket scientists are fighting against. It's more efficient, as to make it more commercially available. You see, back in the day, this was in 2012, this was a very bad ratio. Now it's improving. So our liftoff was May 16th, 2011. Sorry, I said 2012, apologies. 2011 is when we went to space from Kennedy Space Center in Cape Canaveral in Florida. And here you see we were installed on the International Space Station on the 19th of May, 2011. AMS is an international collaboration based at CERN because the outlook of AMS is very similar to what we do at the Large Hadron Collider. And almost all these physicists coming from so many different countries also at some point in their lives worked also on collider experiments. Here you see it's an international collaboration from Portugal, from Spain, from Brazil, from Mexico, from the United States, from France, from Netherlands, from Finland, and here we are also from Turkey. We have a large number of collaborators from China, as well as from Taiwan, which is already a success of science diplomacy. Here you see our reason for doing fundamental science on the International Space Station. So if you think about it, there are two kinds of cosmic rays traveling through space. One of them is neutral cosmic rays, are light rays and neutrinos. And light rays have been measured, for example, by Hubble, now by JWST, almost 50 years. And several fundamental discoveries have been made. As for charged cosmic rays, after the pioneering experiments with balloons and small satellites, using a magnetic spectrometer on the International Space Station is a unique way to provide precision, long-term measurements of high-energy charged cosmic rays. And this has only been done in the last 10, now 20 years. So we hope to continue doing this until the lifetime of the International Space Station. We hope will last after 2030. So here is the control room of the alpha magnetic spectrometer at CERN, called the POCC, POC for short, Payload Operations and Control Center at CERN. And now today I have a student, Bilge Demirköz, who's actually sitting at this desk. My PhD student is right there right now, taking the shift. So we follow and we watch what's going on the International Space Station every minute, every second, and we follow up with NASA and make sure that our operations are perfect. And this goes on 24/7 without any holidays. So as I mentioned, in 1912, Dr. Hess went up on a balloon, and on this balloon, he found that as you go up to space, radiation dose increases and increases. He went up to 5,000 tons, risking his life without an oxygen tube. And later, positron, which is the antimatter of electrons, was discovered in 1932 while cosmic rays were studied. The pion, which is was the first subatomic particle to be discovered, was then discovered here. Also like this, from the pion, the muon, the electron, this decay chain was discovered in cosmic rays. And the muon, the kaon, lambda, C, sigma was discovered also in cosmic rays. And you see these dates. But these were discovered using the showers. And now we are in space for the first time. So in space, since these experiments were all done either on the Earth or on balloon. And on the International Space Station now, instead of seeing the shower, we see the primary cosmic ray. So what do we use? Is we use precision and multi-purpose spectrometer. So I don't want to go into too much detail about particle physics, but I do want to give you a flavor. What we do in science, we do, and we do it multiple times. So what do I mean by that? So for example, this radiation detector at the top, this is called the TRD, transition radiation detector. So on this detector, we can identify whether the passing particle, the particle comes from the top and goes to the bottom, as it passes, whether this is an electron or positron. And then we have a silicon tracker. And this tracker layers are here identified in pink. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 layers of silicon tracker. And the silicon tracker can figure out where the particle passed through within something that is about 1/10 of the size of your head. So we know exactly where the particle went through. Why is this important? The reason it's important is because we have a tracker, and this tracker is inside a large magnet. So this magnet, this case outside of the tracker is the magnet here. And we have a magnetic field like this, sideways, so that when the particle is passing through, it curves either this way or it curves this way. So it curves either clockwise or counterclockwise. From how much it curves, we can measure its momentum, and from the clockwise or anti-clockwise, we can figure out its charge. So whether it's negatively charged or positively charged, whether it has a charge of 1 or 2 if it's helium, or for example 6 if it's carbon. So we can identify the different charges, the Z. So we do this with a combination of the silicon tracker and the magnet. So at the top and the bottom of the tracker, so here in green, these layers in green, we have what is known as the time of flight detector. And this time of flight detector is exactly what it says. It measures the time of flight of the particle through these two planes. What do we learn from that? We also learn how close the particle is going to the speed of light. So we have an understanding of its energy, as well as we have an understanding of its charge from the amount of charge it deposits in these time of flight layers here. At the bottom, we have what is known as the ring imaging Cherenkov counter. So this uses the Cherenkov effect, using very light rays, very light materials. And what we see in this also is we have a measurement of charge of the particle as well as its energy. And at the very bottom, which is known as the electromagnetic colorimeter, again, at the very bottom. So we have this electromagnetic colorimeter at the bottom, also measures the energy of positrons, of electrons, and of gammas. So what I want to emphasize, while you may not have understood, of course, the particle physics behind this, what I want to emphasize is that in physics, and in science, we do something many times. We make many measurements. We don't trust one measurement. We measure the charge of the particle, measure independently the momentum and the energy in different detectors, in the tracker, the rich, the ECAL, and TÜV, so that we have at least four independent measurements, so that we, at the end of the day, we really trust our measurements. So here is an example of a particle that passed through our detector from the very top to the very bottom. And for example, at the top, as it passes through the TRD, you see that it identifies as an electron, and then it goes through the tracker and the magnet. We measure the momentum, and then here we measure the charge again, and here at the end we measure its energy. At the end of this whole measurement, we make a distinction, and we know that it's a 424 giga electron volt positron. Now you might say, what is a giga electron volt? Well, in particle physics, we quit using joules a long time ago. Instead of using joules, we use giga electron volts, mega electron volts, tera electron volts. And the reason is the following. In particle physics, you might know from Einstein that E is equal to mc squared. So that energy is very similar to mass, or mass can also be thought of as a form of energy. So when we talk about an electron, as it goes up through 1 volt, has an energy of 1 electron volt. So 1 electron volt is if 1 electron goes up 1 volt. That's the energy unit that we use, electron volt. Now, for example, a proton has a mass of 1 giga electron volt. Okay, a positron, for example, has a mass of 500 kilo electrons. So this is a positron now, and it has an energy of 424 giga electron volts. So this is very high energy, and this is actually generally the limit for what the Large Hadron Collider at CERN can also produce. So we are working in very similar regimes as the Large Hadron Collider. At very high, this is the high energy frontier of particle physics. So why do we study this? We study it for many reasons. One of the reasons is we have found an excess of positrons in space. What do I mean by that? We have found many positrons at high energies, and we are now studying to understand why we have such an excess of positrons in space, and how to make it understandable. So because what do I mean by understandable? These excess of positrons can come from two sources. Either it can come from dark matter, or it could come from, for example, pulsars. So we are understanding, we will be running for another 10 years on the International Space Station, the hope to understand what the source of these excess of positrons are. And we are going to have an upgrade in space. We're going to have astronauts going on a spacewalk and giving us an upgrade in 2 years. So we will have more detectors at the top of this that will give us an even higher energy rate. The other reason why we study this is we want to understand the space radiation environment around our Earth. What do I mean by that? The Earth has a magnetic field. And because it has a magnetic field, charged particles, get trapped around around our Earth. You might know that when a charged particle crosses the magnetic field, it bends. So because it bends, and our Earth has a magnetic field, when a charged particle comes, it goes into an orbit. It can go into an orbit around the Earth. So in different parts of the orbits for the Earth, we find different amount of radiation. For example, at low Earth orbit, which is where most satellites are, you might know of Starlink, now quite famous. These satellites, these Earth observation satellites and telecommunication satellites, are mostly at this low Earth orbit, or LEO. And here you receive about 1 to 10 kilorads of equivalent dose in silicon per year. In MEO, the middle Earth orbit, and middle Earth orbit is where the GNSS satellites are. So for example, GNSS means global navigation satellites. So these are, for example, GPS satellites or GLONASS satellites. These are the satellites that tell you where you are when you open Google Maps and you figure out where you are, you figure out your GPS coordinates. So these satellites live generally in the middle Earth orbit. And up there in GEO, which is geostationary orbit, these are where the TV channel, the satellites that provide TV channels reside, so that you don't have to move your TV dish, and the dish always looks at the same spot in the sky. These are at 36,000 kilometers. These receive about 10 to 100 kilorads per year. So that's interesting. So if you look at the dose that a satellite receives versus the altitude, you see this camel's back. And this camel's back is because the Earth's magnetic field is not uniform. The Earth's magnetic field, the Earth is not, for example, a sphere. It's like more like an orange, a bit pushed from to ends. And also the rotational axis of the Earth does not align with the magnetic center of the Earth. So there's an angle of 11 degrees between them. And this makes for a bit of an asymmetry in the orbits of these particles around the Earth. We also see that there is an effect from the sun side and the shadow. So this is the sun facing side, and because there's a solar wind pushing this way, you see particles are swept towards the night side. So this is the night side, this is the day side of the sun. So there's also an asymmetry between day side and night side. So this is very interesting as well, because we are now sending thousands of satellites to space per year as humanity. We want to go to Mars, we want to go to the moon. And if we want to live in space for longer, we have to understand this radiation dose. And as you know, radiation can cause cancer, can cause cataract, can cause other problems, human bone loss. And so this space radiation environment is important if you want to be spacefaring race, as well as for our satellites. So what kind of radiation effects are there for electronics? So first of all, there is total ionizing dose. And total ionizing dose is the amount of electrons that are ripped from materials as radiation is impinging upon the material. The second is the non-ionizing effects, which means that these particle comes and actually unhinges a nucleus from the crystal lattice. So you really break the bonds in the lattice, crystal lattice, for example. And the other effect that you can have is single event effects. What does that mean? So almost everything is now digital. And when a particle passes through, it can create enough charge in your electronics, in your digital electronics, to make a 0 into a 1, or it can make a 1 into a 0. So, or it could rupture the gate completely. So these are very important, especially for semiconductor electronics, of course. So you have to understand these radiation dose effects. So we are working on understanding these radiation dose effects. So the first one, which is the total ionizing dose effect, you can test for this using a large cobalt-60 source. Here we have one in Ankara. It's a huge source, and we can make TID tests, these total ionizing dose tests. And here is our team with the Aselsan, one of the largest producer of electronics in Turkey, for space applications. We tested SSPAs, solid state power amplifiers for space using this source. The other thing that we built now in Turkey for single event effects is we have built with our team, we built a beamline at an accelerator. So in Ankara, we have a Cyclone 30. It's a 30 MeV proton accelerator. And this accelerator was built for radiopharmaceutical production in 3 different rooms, in a solid, a gas, a liquid target room. Here's the accelerator with 4 different beam lines. And we are in this room at the end of this beam line. And we built a radiation facility here. Here is our design, and built this, and now we are performing single event effects. So the test that I mentioned here, we can now test electronics for single event effects using protons. So let me show you what we built. So with CERN's help, with science diplomacy, we became an associate member of CERN. And using this associate membership, we worked with CERN to build, first of all, the infrastructure for beam optics in Turkey. We built the vacuum system, the robotic system, the test and measurement system, the control system, and the cooling system, all in Turkey. And these were all firsts for our country. For each measurement and calculation, we used at least 2 different simulation programs. And here is the beamline as built. This is now commissioned and is working since November 2019. It cost us about 1.5 million euros to build this facility. And at the end of this, we have now tested 24 tests. We have performed 24 tests for different labs, for companies, for research institutions, for CERN. We are testing electronics here. And what you see here is we have a beamline under vacuum. These first 2 magnets we bought from Norway, and this one we built ourselves. And how did we do that? We did that because we became an associate member of CERN. Here's our former Minister of Energy. Here is our former Director General of CERN, Rolf Hoyer. And here's our ambassador to the United Nations. And this was signed on the 12th of May in 2014. And because we became an associate member of CERN, we could learn from CERN several technologies. So one of the most important things we did is we designed an industrial-sized particle magnet for an accelerator here at, in Ankara, at METU. The design was done with our engineers, and then a company in Turkey built and made this magnet. And then this magnet was tested at TÜBİTAK. I believe you're going to be visiting TÜBİTAK tomorrow. At the Metrology Institute of TÜBİTAK, and then we took it to CERN. So, and then these are done at CERN. these tests were done at CERN, and it was tested at CERN, and you can see this on the magnet. This is from the this is stickers on the magnet, and this quadrupole was tested at CERN and certified by CERN. And now this company, Sömmerstrafo, is now building magnets for an upgrade to CERN. So this was a perfect example of science in the sense that we first transferred knowledge from CERN to Turkey. We built up technical expertise using that knowledge. We transferred that out to a company, and now this company is producing magnets for doing further research at CERN. So this is the scientific loop, the scientific closed loop that should exist between science and industry. Another thing that we did is at the end of this, okay, they've done a lot of things, but I want to give I wanted to give two examples. The other example I want to give is another success story, and you see this testing area at the end. This is a robot, and it moves the sample in and out of this testing area. And what we do there is we measure the testing area, the amount of radiation dose received, and we do this with 3 different detectors. We do it with scintillators, with diamond detectors, and with silicon detectors. And because we wanted some silicon detectors, we got also some from CERN, but we learned that TÜBİTAK Bilgem, which you will visit again at TÜBİTAK, they're also producing silicon detectors. So but they're doing this for photons. So we got some silicon detectors that TÜBİTAK Bilgem was building, and we decided we want to try this to see if we can see particles with them, and this was successful. And then we decided, oh, this is interesting, so let's use it for other purposes. Let's use these silicon sensors to measure. And at the time, it came to our attention that Turkey also started its own space program. And for the Turkish space program, we built a radiation monitor. So here you see a little box. This is a very small detector, nothing like at CERN, nothing big. Yeah, this is only half a kilogram. And inside this box, you see DEDA 3. These are silicon detectors built by TÜBİTAK Bilgem, but the readout was built in a collaboration between our institute and TÜBİTAK Bilgem. Here is our card that was designed in-house and produced in-house, and then the readout, and here is the box. On the outside, we also have a Geiger counter, and this then went up on 2 sounding rockets. Now, for those of you who don't know, what are sounding rockets? Sounding rockets are rockets that make a parabolic flight. So they go up, and then they go to space, and then they fly a little bit in space, and then they fall back down to Earth. Why are sounding rockets good or interesting? Sounding rockets are very good if you want to test things before you go to space. It's all countries which have gone to space, for example, even SpaceX, first made sounding rockets to test electronics, to test communication, to test the burn of their rockets. So Roketsan, which is one of the 2 main carriers of hopefully satellites in Turkey in the next decade. 2 years ago, they were going to make a sounding rocket flight, and we went up space with them from Sinop, from the Black Sea, and then we fell into the Black Sea, and we actually took data with Roketsan on this flight from space. So I want to now show you this flight. We went up to, so for those of you who are not familiar with space, the limit of space defined when wings do not anymore work. So if you have some wings, and with these wings you can still navigate, you call this atmosphere. And if you can no longer use wings, and having wings buys you nothing, then you call this space. So this limit is called the von Karman line, and the von Karman line is at 80 kilometers. So this is internationally recognized line of atmosphere and space. And so we went up to 137 kilometers on this maiden flight. And I want to show you the flight first before I show you some, before I show you why we did this, I want to show you why we did this. So why is it interesting? So on the y-axis here, you see the altitude, and on the x-axis here, you see the flux. And you see this, the flux on the x-axis is logarithmic. So what you see is as particles come from space, they collide with some air molecules, and then they shower. And the shower, at some point, reaches a maximum, and then things decay. So the maximum of secondary particles is, you see there's a maximum here, and it's about 20 kilometers. And this is called the Renneger-Filter maximum. And it's not easy to measure this so much. Why is this? The reason is the following. Flights, human airplanes generally fly at 10 kilometers or 15 kilometers. And balloons go up, but generally explode, these weather balloons explode around 30 kilometers. And the thing is, so here's, you see this better actually. This is the same graph actually. On the x-axis, you see the dose. On the y-axis, you see the altitude. And what you see here is this data here. You see data, this red and this black line. They're collected by balloons. And it's balloons up to 37 kilometers, because this is, the balloons generally explode at 37 kilometers. And now when you go to space, well, okay, so the lowest altitude satellites are around 300 kilometers. So you have, again, a lot of data after 300 kilometers, and then you see this famous back of the camel. This is the camel's back, yeah, which I showed you earlier. But you see, there's not much data here. Why is there not much data there? Because between 37 kilometers and 300 kilometers, nothing can stay there for long. There's no way to collect a lot of data because the only things that you only travel with rockets between these two areas, and if you're below 300 kilometers, your orbits will decay very fast, and you'll fall back down to Earth within a week. So mostly we never send satellites up to 300 kilometers, because at 300 kilometers, there's still enough resistance from the leftover of the atmosphere that eventually your orbit decays and you fall into the Earth. So generally, you send things, you make orbits above 300 kilometers. So this is why there's no data there. So this was very interesting to make this flight on a sounding rocket to measure up to 137 kilometers. And I would like to show you a video of this.
Ateşleme için son 5, 4, 3, 2, 1, ateş!
right, so what do we find in this flight is we saw this maximum at 20 kilometers here and there in the Geiger counters. In the silicon detectors, we had very few events because the silicon detector is under the cover. We want to cover them and to protect them a little bit from the space environment. And we have very few statistics, so you cannot see this maximum. As this flight is short, as you go up to 137 kilometers and you fall back down. But we proved that this detector works in space, and now we're getting ready for the next flight, which is next year in 2023. We plan to go up to 300 kilometers, again with a sounding rocket. And in 2026, we will have our first satellite with Roketsan flying into space. So this is our group, and before I finish my talk, I want to talk about my group, because I didn't do all of this by myself. It's a group effort. Nobody can do this by themselves, obviously. And we have a beautiful group. Our graduates now are at very prestigious institutes. We also have an international team. Right now, one of my students from for example, Pakistan, he's now at CERN the next 10 days. So this is a group effort, and I want to emphasize the importance of international collaboration and knowledge transfer and sharing is very important. We want to go further in science and in space. So here is again some photos from the accelerator team. Here's my team and our reports to the funding agency. You see the folders. Also good. I find that good report is very important, and I would like to thank the Presidency of Strategy and Budget for financing us, for the Presidency of Defense Industries for their collaboration, and to Roketsan for the flight, and to the TEMMAK Proton Accelerator Center for their wonderful collaboration. And I would like to thank you very much for listening to me. I'm very sorry about not being there. I would love to meet you in person, but I will be very happy to answer your questions should you have any questions to me. Thank you.